Now that we have algorithms that together can solve AX equals B, let's go and look at what the cost is of these algorithms. To analyze this, we need to partition our matrices and our vectors. Now actually we don't need this, so we can ignore that. And think about the algorithm that computes the LU factorization overwriting A, where below the diagonal we store L. We don't store the diagonal of L because it's all ones, and then on and above the diagonal of A we store upper triangular matrix U. The computations we have to perform in each iteration are given here. The question now is, what is the cost of each of those operations as the algorithm proceeds? Now remember that the algorithm proceeds from the top left to the bottom right. And notice that initially this top part here is 0 by 0, and by the time we're done, we will have swept through the entire matrix. So we're freezing here a moment in time when we have done k iterations already, and k then is given right here. This matrix is k by k. This is always one row and one column, so we'll put a 1 there, and then what's left are n minus k minus 1 rows and n minus k minus 1 columns. So this gives you an idea of what the different sizes are that we encounter. This right here is typically implemented as 1 over alpha 1, 1, because a division is actually very expensive, so you want to do it once, and then you take the result of that and you multiply it times the vector A 2, 1. Let's ignore the division, and let's instead focus on all of these multiplies. A21 has n minus k minus 1 components, so we are performing n minus k minus 1 floating point operations here. This here is a rank 1 update. And remember that in a rank 1 update, each element in the matrix being updated is updated by doing a multiply of the corresponding element in the first vector times the corresponding element in the other vector. So that means a multiply and, well, in this case it's a subtract, but let's call it an add to update each individual entry in the matrix. So that means 2 floating point operations. And then you need to ask the question, how many entries are there in that matrix? Well, we know how many rows it has and how many columns it has. That's given here and here. And therefore, we know it's 2 times n minus k minus 1 squared. So, in the current iteration, we're performing n minus k minus 1 squared times 2 floating point operations for the rank 1 update. And we're performing n minus k minus 1 multiplications to compute the multipliers, or however you want to refer to it. Now, among friends, this cost is very small relative to that. Well, it probably isn't when k is large, but most of the time k is going to be small. K is going to sweep from 0 to n. Trust me, this particular term is not all that significant. If you want, you go and work out what the contribution of that term is to the total. So let's erase that term. That leaves us with that. Notice that k goes from 0 to n minus 1. And this is just the cost when k has some given value. So what we really need to do is we need to sum all of this up from k equals 0 to k equals n minus 1. And that gives us then our total cost. The 2 we can bring out. Now the other thing to notice is that if k goes from 0 to 1 to 2 and so forth, n minus k minus 1 goes from, let's see, n minus 1 to n minus 2 and so forth. Notice that k, the biggest it gets is n minus 1, and therefore the smallest n minus k minus 1 gets is 0. So what we can do is we can think of this summation as being the sum from j equals 0 to n minus 1 of j squared. But that's something that we saw in week 2. If you go back in your notes, you will find that that's equal to 2 times n minus 1 times n times 2n minus 1 divided by 6. This whole mess is approximately, 2n cubed, and therefore everything here together is roughly, where can I write it down? 2/3 n cubed. So roughly the cost of performing an LU factorization is 2/3 times n cubed. Let's have a look at the cost of solving LZ equals B. So what I did here is I put Z here, B here, and L here. And recall that if we overwrite B with Z, then the update that happens in each step is this right here, and we recognize that as an XB. Okay? Now again, we went and we indicated what the different sizes of the matrix were. So if we ask the question after k iterations, what is the cost of the current step, then notice that L21 is of size n minus k minus 1. So you're performing an XB with vectors of length n minus k minus 1. The cost of an XB is 2 times the length of the vector, so that's n minus k minus 1. And again, we need to sum this over k equals 0 to n minus 1. And again, we can do the trick of recognizing that we can instead sum this from j equals 0 to n minus 1, 2 times j, which of course we can write as 2 times the sum j equals 0 to n minus 1 of j. But that's something we saw in week number 2. This summation right here is n times n minus 1 divided by 2. If we then have to multiply that by 2, we get that this is equal to n times n minus 1, but that is approximately n squared. So we see that solving a lower triangular system requires roughly n squared floating point operations. Moving right along, I actually set this slide up slightly wrong, because remember that when we solve an upper triangular system, we actually march through the matrix backwards. So after k iterations, this really should be of size k. This should be of size n minus k minus 1. This should be k. And this should be n minus k minus 1. This is the update that is performed. What is this? This is a dot product, but it is a dot product with vectors of size, let's see, the size of this vector here is k. So this step right here requires 2 k floating point operations, and then we have to do one divide, but that one divide is probably insignificant relative to the rest of the cost. If you want to go and compute how that contributes, that's your business. You can go ahead and do that. So now we have to sum that over k equals 0 to n minus 1, because k ranges from 0 to n minus 1. We can take the 2 out. And this is again something we recognize from week number 2. That equals 2 times n minus 1 divided by 2, which is approximately n squared. In order to solve ax equals b, what you do is you do an LU factorization, which costs 2/3 n cubed floating point operations, and then you do a lower triangular solve and an upper triangular solve, each of which costs n squared floating point operations. Now notice that relative to 2/3 n cubed, if n is large enough, let's take n to be 1,000, these terms here are insignificant. So roughly, solving ax equals b requires 2/3 n cubed floating point operations. Now, if you then get a new right-hand side at some point, and you have stored your L and your U, then you don't need to refactor your matrix A. All you have to do is solve Ly equals B and Ux equals Y, and therefore for every new right-hand side that shows up, all you need to do is 2n squared more floating point operations. Now, there are other ways of solving Ax equals B. There are ways of taking advantage of zeros that are in A, which is known as A being sparse. Let's not talk about that in this course. That's a different course.